Welcome to our webinar, How to Choose the Right SSD for Your Industrial Application. Let's have a look at today's agenda first. We are going to look at a little comparison between SSDs and the classical hard disk drives, give you an overview of our flash technology and the different types of flash memory employed today, how controllers and firmware of SSDs increase their lifetime, what write amplification on an SSD is, how to judge the different metrics for comparing SSDs, how wear leveling works, and how to use predictive maintenance to find the lowest total cost of ownership for your SSD, followed by a conclusion. While SSDs are now mainstream, several applications still use hard disk drives, usually for cost considerations. Let's compare SSDs with HDDs first. HDDs have mechanical components and moving parts, while SSDs have not. SSDs, by their very design, support random access to data, while HDDs can only access data sequentially. It's also very difficult to design HDDs for operating in a wide temperature environment, which is much easier for SSDs. The speeds of HDDs are usually quite a bit slower than on SSDs, and shock and vibration have an impact on performance even within acceptable limits, while SSDs suffer no degradation of performance when in a vibrating environment. Let's have a look at flash technology. There are currently 6 different types of flash memory in use for SSDs, and they all have their specific strengths and weaknesses. For industrial applications, SLC, ISLC, MLC, and 3D TLC are in use, while consumer and data center applications also use QLC and PLC SSDs. So what are these? SLC is the classical type of flash memory. It only stores 1 bit in each physical cell on the media and provides the most write cycles of all flash types. It is a very good choice for write extensive applications, especially when you have no control over write amplification. It's also very expensive. MLC SSDs store 2 bits per physical cell by using 4 different voltage levels to represent them. They have been basic for most SSDs for about a decade, and they're usually not write cycle limited in a way that impacts applications. They also have much lower cost than SLC SSDs since they only need about half the silicon space to store the same data. As a compromise between SLC drives and MLC drives, there's also ISLC, pseudo-SLC. These use the physical flash media of an MLC drive, but only store 1 bit in each cell, much like SLC SSDs. The durability is then between those 2 types, and while the price is higher than MLC, it's a lot more cost efficient than SLC SSDs. Mainstream today is 3D TLCs, storing, just like the name implies, 3 bits per cell. They also made use of advantages in manufacturing and using 3D structures within the silicon wafer. This allows for larger cells for data storage and increases the signal-to-noise ratio. Therefore, even using 8 different voltage levels to represent the data on the physical media, they barely have any loss of durability due to the 3D structures. They are now mainstream and very cost-effective at less than half the cost of MLC SSDs. They are also suitable for pretty much all applications and to be used as an MLC replacement. QLC, quad-layer, and PLC, penta-layer cells, are not yet ready for industrial use. They are, however, useful for consumer and data center applications. They can store 4 or 5 bits per cell, and that comes at the cost of losing significant write durability. QLC SSDs can be recommended for consumer applications and desktop use, while PLC SSDs target nearline storage as an HDD replacement. Since those HDDs are usually rarely written to, the loss in write durability does not have a downside here. There are also no wide temperature spec SSDs made up of flash memory of these types. In this summary, you can see how the different flash types compare in the most important metrics: cost per gigabyte, durability, and their suitability for wide temperature applications. Let's have a look at how controller and firmware increase the lifetime of your SSDs. Flash memory uses much larger blocks than HDDs. While HDDs usually have the classical 512 byte sectors, SSDs have sectors of 256 kilobytes for the most part. Most operating systems were designed not just with the behavior of hard disks in mind, but also assuming classical 512 byte sectors. Since HDDs have essentially unlimited write cycles, read, modify, write, even for single bit changes, is limited on HDDs only by their speed. Since HDDs have essentially unlimited write cycles, even modifying single bits on the media will not degrade an HDD's lifecycle, and the performance will only be limited by mechanically moving the read-write head on the media. On an SSD, on the other hand, writing lots of small data packages does not impact the performance that much, but does decrease the expected lifetime. The phenomenon of writing a lot more data than the application actually wants to write on an SSD is called write amplification. Write amplification happens when you change only, for example, a single bit in a file and write it to your SSD. Since the block size of an SSD is usually 256 kilobytes, this means that in order to write even a single bit to your file system, an SSD has to load 256 kilobytes from the flash media, modify a single bit, and then write 256 kilobytes back to the flash media. So even the smallest write access consumes 256 kilobytes of the total write lifetime of your SSD. This can become a problem for your SSD's lifetime if your application writes a lot of logging information at a high frequency. Applications that take this into account can dramatically extend SSD's lifetime, for example by consolidating several log files into one large log file or collecting data in memory and writing it in consolidated 256 kilobyte blocks. When comparing SSDs to make a decision which one to employ in a certain application, many users compare the drive writes per day. This metric has become very popular for comparing the lifespan of SSDs, but only applies between drives of the same size. The value essentially describes how many times you can fill your SSD every day during its warranty period before it gives out. If you multiply that value with the warranty period in days and the capacity, you get the total writes that are possible. Those are usually referred to as the total bytes written. If you know how many gigabytes per day your application is going to write, this allows you to determine the expected lifetime of your SSD in your given application. However, due to write amplification, there is no correlation between the amount of data that your application wants to write and the amount of data that is actually written to your physical media. One of the methods that your SSD controller and firmware employ to extend the lifetime of an SSD is called wear leveling. File systems tend to write to some sectors more often than to other sectors. For example, the boot sector may be written to more often, or the sectors that represent your page file on your media. Due to the limited write cycles an SSD has to offer, this could quickly degrade certain sectors and destroy your SSD in the process. Wear leveling attempts to distribute logical writes across the entire physical medium to preserve your SSD. There are two major ways of implementing wear leveling. There's dynamic wear leveling, which is easy to implement and has little overhead, and there is static wear leveling that offers better performance. On an SSD without wear leveling, those frequently used blocks I mentioned earlier would be written to the same physical block all the time, and as mentioned, quickly use up its write cycles. Dynamic wear leveling keeps a list of the yet unused blocks on the flash media, and each time a write operation is done, it reads the block you want to modify, modifies it in memory, and then writes it to one of those reserved blocks. The previously used block is now added to this buffer list. However, if your SSD is almost full or under other circumstances, this could lead to the wear leveling algorithm simply exchanging one block with another block from the buffer list all the time and using up those blocks' write cycles while other blocks remain unused. This problem is addressed by static wear leveling. It also uses a system buffer block list like the dynamic wear leveling, but also has a counter that tracks how many times each flash block has been written to. The algorithm on the right shows you approximately how this algorithm works. Whenever you want to write a block, it checks the next block on the system buffer list, compares the number of writes this block has had with the average across all the flash media, and skips the block if it already has more writes than the average, and chooses the next one. This process continues until the algorithm finds a block that is below the average and uses this one. As a result, all blocks across the media are used equally. Since write amplification determines your SSD's lifetime, and you have no control over write amplification, for example in third-party applications or the operating system, it is always a good idea to check what is really going on your SSD. Wear leveling algorithms and the old smart interface connect a large amount of data. That can give you an insight on how your application and operating system are loading your SSD. Systems such as iSmart can use that plethora of data to determine the lifetime of your drive in your application with sufficient accuracy. And you can use this prediction to find the most cost-efficient drive for your application. As a conclusion, there is no best SSD type. Which SSD is right for your application depends highly on how your SSD is used. We highly recommend to use predictive tools to match the SSD lifetime to your project needs, and to avoid using an SSD type that only drives up your cost without increasing your appliance's lifetime. While many customers tend to use SLC or MLC drives just to be on the safe side, using predictive tools often yields a result that TLC SSDs are just as suitable for almost every application and most use cases than the other types. And as previously mentioned, TLC SSDs also offer the lowest price per gigabyte for industrial applications. When choosing your SSD, you should also keep in mind that an SSD with a larger capacity always has an increased lifespan compared to the smaller type. Twice the size, twice the lifespan in the same application. We would therefore highly recommend to use predictive tools in a field test environment to see what you really need from your SSD in terms of write cycles and capacity. If you need any further information on the subject, please don't hesitate to contact us.